Good morning, all of you. Today we are going to start our classes. Now I think only 10 students are there in the class. Anyhow, we can start the class, and those who come late can um, see the videos and study by using these videos. These videos I will upload in Moodle soon. For the time being, I am giving you by using the Google Classroom. Okay, the first module is Lagrangian formulation. Lagrangian formulation. As we have discussed in the previous class, previous Google Meet, so far we are using Newton's laws or Newtonian mechanics, and why we are switching over to Lagrangian mechanics. There are some reasons, and the first one is regarding the constraints. Constraints. What are constraints? Consider a body moving from top to bottom, a body falling freely. It will fall freely in a straight line towards the earth. It cannot move upwards. It cannot move along horizontal directions. It can move only vertical direction downwards. Therefore, the motion of the body falling freely is restricted to move along a straight line downwards. That is a restricted motion, and the motion is limited by means of some restrictions. Limited by means of some restrictions. Consider a simple pendulum oscillating. There is certain restrictions to the simple pendulum. The length of the pendulum cannot be changed. It is a constant. Okay. And the oscillation is only along a plane. It cannot oscillate in a circle. It is restricted to move only along a plane. Therefore, it is a restricted motion. But a bird flying, it is not that much restricted. It can move along anywhere in the space. Therefore, it is not having certain restrictions based upon the directions or coordinates. And a body, an ant moving along a sphere. There is a ball, an ant is moving along the ball. It can move only on the circumference of the, or only along the surface of the sphere. It cannot move up, or it cannot move into the sphere. Therefore, there are certain limitations for most of the types of motions, and when there are certain limitations or some restrictions, these restrictions are called constraints, and the motions are called constrained motions. Constraints are the limits which limits certain restrictions for the motion or for the state. For the state of a body, for a rigid body, there are certain limitations. For a rigid body, the particles can move only together. Two particles cannot move separately, it can only move together. Therefore, certain limitations are there. These limitations are called constraints. Constraints are the limits which offer restrictions for the free movement of the particles. And because of these constraints, there may be so many constraints for a body. There are different kinds of constraints may be there for a single system, and considering all these constraints, it is very difficult to use Newtonian mechanics. It is very difficult to apply all these constraints to the Newtonian mechanics. Therefore, we are switching over to Lagrangian or Hamiltonian mechanics. That is one reason for considering Lagrangian or Hamiltonian mechanics instead of Newtonian mechanics. And now we have to study something more about constraints. We can classify constraints broadly into two. There are different types of classifications. Now, for the time being, for our purposes, we are considering a certain classifications only. One is holonomic and holonomic constraints, and another one is non-holonomic constraints. You might have studied in your degree classes about these classifications, constraints, degrees of freedom, etc. And holonomic constraints are, for example, consider an equation of a sphere x square plus y square is equal to c square. Or another equation of a simple pendulum. What is the equation of a simple pendulum? Second order differential equation of a simple pendulum, d square y by dx square or dt square plus omega square y is equal to 0. This is the second order differential equation of a simple pendulum. And another equation of a plane, ax plus by plus cz is equal to k. It is an equation of plane. These all are certain formulae which represents certain motion. These all are certain formulae which represent certain motion. These formulae can be expressed as equations or by means of equal sign. Equation means there should be an equal sign, there should be some quantities before the equal sign and after the equal sign, on the left hand side and right hand side. Therefore, these are equations represented by equal signs, and if a motion can be expressed in the form of an equation, that is called holonomic constraint. If it cannot be expressed in the form of an equation, then it is called non-holonomic constraint. Or if the system can be expressed by means of an inequality sign, inequality sign, that is called non-holonomic constraint. Consider a particle inside a box. Consider a particle inside a box. It can move along the x direction from 0 to length L, and it can move up to 0 to breadth B, and it can move, if this is thickness, it can move from 0 to h is the thickness. Therefore, the particle can move x, y, z or z directions. It is free to move along all these directions, but there are certain limitations. It cannot move above the boundary. It cannot move after the length L. It can move along the x direction only up to length L. Therefore, the movement along x direction is from 0 to L, equal to or less than 0, equal to or greater than 0, or equal to less than L. Along y direction, it is in between 0 and breadth B. Along z direction, it is restricted to move along 0 and thickness h. Therefore, these are the formulae which represent the restricted movements of particles inside a box. Therefore, the particle inside a box can move only along these by using these three formulae. They cannot be expressed as equations. They can be expressed only by means of such notations. Therefore, they are called non-holonomic. Such motions are called non-holonomic constraint. The particle inside a box is in non-holonomic constrained motion, or the force acting on this particle is called non-holonomic constrained force. We are not considering that much regarding the non-holonomic constraints. We are more interested on holonomic constraints, and holonomic constraints can be again classified into two categories. They are holonomic constraints can be again classified into two categories. One is scleronomic constraint, and rheonomic constraint. Scleronomic and rheonomic constraint. That is, consider two equations. For example, x square plus y square is equal to L square. Another equation, x square plus y square is equal to L of t whole square. What is the difference between these two equations? The first equation does not depend on time explicitly. Second equation depends on time explicitly. There may be some implicit dependence of time on this equation. Sometimes L may be depending on time by means of some other equation, but explicitly there is no dependence of time for this equation. But here it directly depends on time. The L is explicitly depends on time. Therefore, a motion in which the motion which explicitly depends on time is called scleronomic constraint, and which does not a constrained motion which explicitly does not depend on time is called scleronomic constraint, and if it depends on time explicitly, that is called rheonomic constraint. These are the examples. There are so many examples, so many classifications in different manner based on different category. Conservative constraints, non-conservative constraints, bilateral constraints, and so many classifications are there. For the time being, you needed only this much. And now we are going to study another thing, which is called virtual displacement and virtual work done. This is a new concept. It is somewhat difficult to get the concept. If you want more clarification, you can go through some standard textbooks. You get better idea regarding this virtual work done and virtual displacement. For the time being, I will define only these things. Virtual displacement is a very small displacement. It is usually expressed as delta r. It's a vector. But the thing is that there is no actual movement or there is no actual displacement. There is no actual displacement, there is no physical displacement, there is no actual movement of particles, and then that displacement is called a virtual displacement, and the work done because of the virtual displacement is equal to 0. Always the work done because of the virtual displacement is 0, that is F dot delta R is equal to 0. For this is called virtual work done, or for ith particle Fi dot delta Ri is equal to 0, and for total number of particles in a system, sigma I Fi dot delta Ri is equal to 0, or this is equal to sigma I Fi means Fi applied or external force plus Fi internal dot delta Ri is equal to 0. Total force dot delta Ri is the total work done, virtual work done, because of the virtual displacement is equal to 0, because the virtual work displacement does not mean the real displacement. There is no real displacement, there is no real motion of particles, and the work done because of the virtual displacement is equal to 0, and the total force is equal to F applied plus F internal. For ith particle we are considering Fia plus Fii, and Fi internal means, internal force means there are two types. One is the force of constraint plus force of dissipation, and the one force of dissipation. Force of dissipation means some force which get dissipated, just like frictional force, just like viscous force, etc. That is during oscillation of simple pendulum, the oscillation getting stopped because of the friction of air. That is a dissipative force. Such force are called the Fd. That is also an internal force. When we are applying a force, there are two types of restrictions. When for a simple pendulum, when we are applying a force, there are two types of forces internally. One is the constraint force, that is the body is restricted to move along the xy direction, that is the constraint force. Another force is, there is an opposing force, viscous force, which is also acting there, the air friction, that is called the dissipative force. And we can neglect this dissipative force here. Therefore Fi internal means F conservative force. Therefore total force is equal to, we can write F of constraints. Now here one more thing is that for the virtual displacement, the ith particle, for the virtual displacement, the work done because of the constrained force is equal to 0. Total sigma I Fi constrained force is equal to 0. Total work done because of the constrained forces is equal to 0. That is a very important thing regarding the virtual work done. That is why we are applying these things on Lagrangian formulation, because the constrained forces, the work done because of the constrained forces get dissipated. There are constrained forces there, Fc is there, but work done gets 0. In the case of Lagrangian formulation, we are using work done or energy. In the case of Newtonian mechanics, we are using force. Here there is constrained force, there is a complicated force, but in the case of Lagrangian formulation, we are using the work done or energy. There is no energy because of the constrained motion. You got it? I think you got it. I will say once again, that is, in the case of Newtonian mechanics, we are using forces. In the case of Lagrangian and Hamiltonian mechanics, we are using energy or work done. And the complication regarding the motion is the constraints, forces of constraints. Forces of constraints are little more complicated, and we cannot avoid force of constraints, but there is a provision to avoid work done due to force of constraints. And in the case of Lagrangian, we are using work done. There, the force of work done because of force of constraints are get eliminated. Therefore, it is easy to use work done than using force. Therefore, it is easy to use Lagrangian or Hamiltonian mechanics than using Newtonian mechanics from the point of view of constrained forces. Therefore, you applying this one also, here this also get cancelled. Therefore, we can write Fia dot delta Ri is equal to 0. We can write just like this. Now we consider Newton's second law. According to Newton's second law, Fi is equal to Pi dot force is equal to rate of change of momentum, or Fi minus Pi dot delta Ri dot Pi dot is equal to 0, or we can write dot delta Ri is equal to 0. This also we can write. Or for the total number of particles, sigma I Fi minus Pi dot delta Ri is equal to 0. And here Fi means, as we have discussed earlier, Fi means Fi applied plus Fi internal minus Pi dot is equal to 0. Fi internal is equal to, here we have said that Fic dot delta Ri is equal to 0. Therefore here we have to consider only Fia. Total Fi internal is equal to Fic plus Fi dissipated. Fi dissipated work done, we reduce it to 0. Work done due to dissipated force reduced to 0. Work done due to force of constraints also becomes 0 when we are considering the virtual displacement. Then here only Fia. Therefore we get the equation just like this: sigma I Fia minus Pi dot delta Ri is equal to 0. Or we can avoid sigma I for a single particle, and then we get Fi minus Pi dot is equal dot delta Ri is equal to 0. This equation is a very important expression, and using this expression we can derive the Lagrangian form equation. This equation is called, it is named as D'Alembert's principle. Either write sigma I Fia minus Pi dot delta Ri is equal to 0, or we can write Fia minus Pi dot delta Ri is equal to 0. Delta Ri also is a vector. You can write in this form or as a summation. This is called D'Alembert's principle. And another thing we can have from this equation is that we have to get the concept of generalized coordinates. Here delta Ri is a vector, but Fi dot delta Ri means a scalar. It is a work done. And here we can consider, instead of Ri means the position vectors. For a single system we can have x component, y component and z component. 3 components are there. For then if there are n number of particles in a system, there will be 3n number of coordinates. For one particle there are 3 coordinates, x, y, z. For n number of particles there are x1, y1, z1, x2, y2, z2, x3, y3, z3, etc. Therefore there are 3n number of coordinates are there. Therefore we can write, instead of dot delta Ri, we can write xi. Here delta Ri means delta xi, delta yi, delta zi. Instead of that we can write Fi minus Pi dot delta xi is equal to 0. X is not a vector, it's a coordinate. Instead of x, y, z we are representing x, therefore it is not a vector. Therefore we can write this vector symbol also can be avoided, and we get Fi minus Pi dot delta xi is equal to 0, where I is equal to 1, 2, 3, etc. 3n. And xi is a coordinate with 3n number of values. Xi is a coordinate with 3n number of values. It is not necessary that it should be a position coordinate. In the case of Lagrangian formulation, xi is called a generalized coordinate, and generalized coordinate may be of position, of mass, or of any dimension, just like that. It is a generalized coordinate, and we can discuss regarding generalized coordinate and the derivation of Lagrangian formulation in the next video. This much I am taking the class now, and in the next video we have to specifically define the Lagrangian formulation and the equations used to solve problems in mechanics easily by using Lagrangian equations of motion. Before studying Lagrangian equations of motion, we have to study well what is meant by generalized coordinates, what is degrees of freedom. We have studied only constrained motions. Even though there are constraints, there are so many degrees of freedom also. A particle can have different freedoms to move in different directions, and there may be some restrictions. For example, that also I will teach now, degrees of freedom. Degrees of freedom. In the case of a particle, consider a particle, a body here, a particle here, and it has x component, it has y component. Therefore, if the particle is moving from one point to another point along here, it has freedom to move along anywhere in the x direction or anywhere in the y direction. But it cannot move along the z direction. Therefore, the restriction or constraint is y. And there are two degrees of freedom, x and y. The constraint is z, x and y are the degrees of freedom. Therefore, actual degrees of freedom is the actual number of generalized coordinates minus number of constraints. If there are 3n number of generalized coordinates and c number of constraints, there are 3n minus c number of degrees of freedom. Okay. While we are studying rigid body, we will study something more regarding this point. That is, if there are 3n number of generalized coordinates, a body has 3n number of generalized coordinates. I am writing on this board using this chalk, and this writings has 3n number of degrees of freedom. But there are certain constraints. It can be, I can write only along this direction, I can write only along this direction, I cannot write along this direction. Therefore, though there are 3 degrees of freedom, there is one constraint. Therefore, total number of degrees of freedom 3 and constraint 1. Therefore, there is only 3 minus 1 degrees of freedom. Total, there is only 2 degrees of freedom. There are 3 generalized coordinates, 1 constraint. Therefore, generalized coordinate minus number of constraint gives the degrees of freedom. Okay, now I am stopping here, and today you have to do something. First one, I will give a problem. I will give one assignment for you for taking attendance. After this, I will post the question. And another thing, you have to make a note of this much I have taken. You might have textbooks, I think. There are so many textbooks I have mentioned in the last class. You can take Goldstein, you can take Gupta Kumar Classical Mechanics, Arul Das, and some other books I don't remember now. And you can refer those textbooks and write a very detailed notes regarding these points. That is regarding constraints, examples of constraint motions. You can give more examples and classifications. Then virtual displacement, virtual work done, and D'Alembert's principle, then degrees of freedom, and generalized coordinates, and after that degrees of freedom. Your textbooks I will show you. There is one book here. This is one more book, Takwala and Puranik. This is also there in the library. It's not a complete syllabus book, but it's a very good book. You can refer for some of the chapters. You can refer this book, Takwala and Puranik, Classical Mechanics. Okay, and another book. This is a problem solved book, Shom series, Theoretical Mechanics for net purpose. or for gate or net purpose, you can do more problems from this text. I have one book. If anybody of you want this book, I will give for reference. This is the textbook's name is Theoretical Mechanics by from Shom's series. This is a series, Shom series, and this is one book from that. And all other books are in library. So you write a notes for these portions in a particular notebook for classic mechanics itself, and sometimes I will ask you to show the notes, complete notes. So from the first day onwards you start writing notes, and if you want any written notes from me, you can ask. Not complete notes, some of the notes, if for some clarification, if it is not in these textbooks, you cannot find it in the textbooks, I will give you. Okay, and if you have any doubts regarding these portions, you can ask in the WhatsApp group. You can ask personally also. It's open for you, all of you. I hope you can understand everything. Okay, thank you.